Hi guys, so what you see now is the practical version of the JK flip-flop, and I've implemented this from ground up, meaning I've implemented this from scratch on this circuit simulation tool. Now the problem with this is if I implement this from ground up, you might notice that there are a bunch of red signals here, which means that those states are non-determined. They don't know, or the computer or the circuit simulation tool doesn't know what those states are supposed to be. So we have reached this sort of chicken or the egg problem, where what I mean by that is to realize the input for this NAND gate, it needs an output from this NAND gate. But then to realize the output from this NAND gate, it requires an output from this NAND gate, which requires an input from this NAND gate. But then you cannot realize any of those outputs or inputs because they are sort of cross-referential. They are referring to each other, right? So we are reaching this problem where we can't really determine what the Q and Q complements values are. So therefore, this implementation doesn't work. And that's really why when we discuss the truth table, I always told you to assume that J, K and Q, Q complement have given starting values, because without starting values, the gate can't sort of proceed on. It doesn't have any values to go on from that point. So it should be given starting values. How we do that in circuitry is by manually tampering with Q and Q complement to change them to a particular state. And then from that point on, we can make changes to the gate. So I'll move away from the ground up implementation and look at a chip that we have that is effectively the same chip, but now in a simplified form. This is the JK flip-flop chip. The same circuit is inside this chip with a few minor changes. J is the input here. This greater than sign input is the clock signal input. K is the other input. There are two new inputs called pre and clear. There are two inputs that help us manually tamper with the Q and Q complement so that we can make changes so that it can start off with some manual state at the beginning. So at the beginning, we need to input two ones to both the pre and the CLR so that the Q and the Q complement realize two inputs at the beginning or two outputs at the beginning. So they are just inputs that we have to stabilize the outputs so that they can be made changes later on. So forget about pre and CLR. We're not interested in that. We just made those changes. And now the gate is in Q and Q complement such that it's 1 and 0 currently. Now notice how there's a clock signal. The clock signal is ticking. It's ticking 1, 0, 1, 0 at a constant time interval. Let me change this time interval to be not at 1 second, but every 2 seconds so that you can see the changes very effectively. Now what I'm going to do is I'm going to set the gate to high, meaning I'm going to change the Q output to 1. If I want to change the Q output to 1, what should I change? I should set the J to 1, right? The J is our set input. So if I set the J to 1, hopefully Q should turn on. What I'm going to do is I'm going to set the J to 1 when the clock signal is low. And you'll realize nothing happens until the clock signal becomes high. So wait for the clock signal to go low. Okay, now I've set it, but nothing happens. And there you go, as soon as the clock ticked, Q became 1. So let's say I remove this, nothing happens to the signal or nothing happens to the gate, nothing happens to whatever was stored. It's now in the memory state, right? When J and K are both 0, it's storing whatever was previously put in it. Let's say I want to reset the latch, or I want to reset the flip-flop. What can I do? I can set a signal through the K input. Let's do that signal while the clock is low and see what happens when the clock is high. Nice. So as soon as the clock ticked, Q complement went to 1 and Q was reset to 0. So notice our inputs are stabilized by the clock signal, right? So whatever changes we make, those changes won't propagate until the clock actually tells it to propagate through. So that's going to solve the race condition, and it will also solve the fault condition. The JK flip-flop solves the fault condition because when both inputs are 1, it will undergo toggling behavior. Let's actually see that in action. Let's say I turn on both J and K. You'll see that Q and Q complement toggles, right? You can see that Q is 0, Q complement is 1, then Q is 1, Q complement is 0. Let's increase the frequency of this. Let's make this tick every 500 milliseconds, and you'll see those changes happening every clock cycle, meaning every time the clock goes from 0 to 1, the clock or the output toggles, right? So that's what it means to undergo toggling behavior. Now we're no longer in this fault condition where both Q and Q complement have the same values. They are different values, but they are changing each time. Right, so that's all there is to know about the JK flip-flops. practical implementation.